This video is a review of energy, work, mechanical energy calculus for systems where no mass crosses the system boundary. It's definitely assumes that you have some knowledge of work and energy from some previous classes you've taken, but we're kind of put things all together and kind of help you to understand how the big picture works. One thing you may recall is energy is conserved. So therefore the total amount of energy is constant, is neither increased or decreased. But that's only true if my system is everything that exists. So everything that exists had some energy in the past, it'll have the exact same amount of energy in the future. But when I'm typically solving a problem, I'm worried about the motion or energy content of this marker, so I'll call my system on my marker. At some initial time, this marker will have energy in many forms, and you can add up all that energy. So that's the initial energy. If I have, for example, a force from outside the system that acts on it to cause it to displace or to move, then in the final state, the marker can have more energy than the initial state. But whatever energy it gained had to be given from the outside the system, and that outside the system, for example me, I lost the amount of energy exactly the same amount that I gave it. Or for example, if I put this on a hot stove, its temperature the marker would rise and it would gain energy, but that would cost energy from the system providing it. And so, kind of thinking about energy. First, energy is a scalar, so it's a value. And it's not like a force or momentum. There's no directionality term, so it's not a vector. And energy can have many forms. And so typically we want to think of energy as a balance. And I have a very long equation I call equation number 1 right here. And this is kind of a form that help you understand what some initial energy in as many forms. I can put energy into the system or take energy out of the system, and then I'll have some energy of the system at the end state. So that's my energy balance. And I think sometimes helpful to write it out in almost in its entirety, or you should be very careful if you don't include a term, that term is 0 or insignificant. So kind of looking at in the initial state, what kind of forms of energy can I have? So that energy can be transformed from one form to another or transferred from one object to another. So I'm looking at the forms of energy here. So one form of energy is internal energy, and internal energy of an object or my system. So I think for now, a system could be an object, a group of objects. So we'll think about internal energy of a system. So that's the sum of all the potential and kinetic energy of all the molecules in the system at that initial time. And then I could have some kinetic energy, and kinetic energy of my system is, for each object in the system, would be 1/2 the mass of that object times its initial velocity, initial speed squared. So if I have a velocity and I square it, then it becomes a scalar, so therefore it'd be a speed. And if let's say I'll do my problem, most of the problems I'm going to solve for are right above the Earth's surface or on the Earth's surface, and so therefore kind of a convenient way to have a very close approximation of potential energy due to gravity is the mass of the object times the g, the acceleration due to gravity on Earth, and h be the initial height. Typically we've referenced to something, typically we call it above the surface of the Earth. I can have other forms of potential energy. For example, I can have electrical energy and potential like stored in a battery. I'm not going to go into details what that is. I'm going to have one equation here, for example, in a spring. For example, if I have a spring that I took from a pen here, so the spring has, I'm sure it's just in its natural state right now. There's no forces acting on it. So we typically call that the free length. And then if I put a force acting on it axially, so if I push in on it, its length changes, and there's a force that takes for me to move that. K is we'll talk more about that later in another video. That's the stiffness of the spring, so that's the ratio of the force divided by the deflection. For example, that could be pounds per inch. So how many pounds it takes her to deflect an inch, or newtons per meter, or some other value. And then the potential energy stored in it is 1/2 that spring stiffness times the square of the difference between the length of the spring at this initial time minus the free length. So that's kind of my initial energy term summation of my system. And then I can have energy come into the system or out of the system, and energy that comes into or out of the system by a mechanical method, for example by a force, is a work term. And we'll talk later about what that really means. And sometimes some textbooks just say plus work, or some just say minus work, but then you have the assumption when they do that, when they say plus work, then they're thinking about the net force, the net work being into the system. So I like to always write both terms out, because then you can think about all the forces that work into the system and all the mechanical work that takes work out of the system. For example, if I have a force here and I'm pushing in this direction and it moves that direction, then I'm putting work into the system. But if I, for example, have this marker and it slides against a surface that has friction, the force is in the opposite direction as the path that it's going, and that's taking work out of my system if my system's the marker. And then heat can go into the system or out of the system. So I like to write both of them and write plus into the system minus out of the system. For example, and heat is just energy transfer from a hot object to a cold object. And if the system I have, if my system's hotter than the surroundings, then heat will go out of the system, isn't it, in that form. So that's my delta change in energy into or out of the system. And then my final state, so this will balance what my final state is. And my final state can be internal energy in the final condition, kinetic energy in the final condition, gravitational potential energy in the final condition, spring potential energy, electrical potential energy, etc. in the final condition. And this energy balance of my system will be true. Does that mean I solve all problems using energy? No. There may be much more simpler ways using momentum or Newton's laws, for example, to solve for it. But when I use energy, I have to be very careful, because being this powerful, to be able that I also it has lots of potentials to do things incorrectly. For those of you who've taken lots of chemistry, you may be familiar with the term enthalpy. Now, enthalpy is just the sum of the internal energy at some state plus a work term due to where work is the product of the pressure and the change in the volume of the system at the system boundary. And I won't go into details of this, but I just want to be aware of that term. Now, we are going to often solve problems, and this is the form we always want to consider. And you only drop a term in these equations if you know it's zero or insignificant. So for example, for systems where we know the internal energy didn't change, so for example, the final internal energy and the initial internal energy are the same. And also for this equation, you can also think, once you have an equation written with a balance, for example, after you've written it, you can bring this term over to this side and say internal energy final minus internal energy initial, and you can write that would be delta internal energy, so final minus initial. So that's another way to think about it. I like to write it this way out first, because that makes me really think I have something initially, I add something to it, and I have a final, rather than writing deltas, but you could do that. But let's say, for example, what if I said that the initial energy, this marker is my system, and it's stayed the same temperature, nothing's changed to it from the initial time to the final time, it has the same initial energy, and there was no, so therefore, I don't need that for this particular problem, because these are unnecessary terms because they didn't change. Or let's say there was no heat transfer into this object during the time I'm interested. Therefore, there's no energy transfer due to, from a hot object to a cold object. So these turn out to be 0. So taking those 0 and this 0, or make it say the delta here was 0, or the net flow of this into and out of the system becomes 0. Therefore, then I just take this really long equation, which is true, which is what I really have to do, and I can say terms that are insignificant or small, I don't need them anymore. But don't just write this equation in this form and say, oh, here's my energy balance, unless for sure you've already made the assumption, or the problem has told you that the terms you took away are insignificant or essentially 0. But no, if you ever you can't just write equation 2 and say, well, that's true for any system that ever exists, because it's not, because you made certain assumptions you got there. Now, for systems, this equation is certainly simpler. There's a term we need to define. It's called conservative forces. And for conservative forces, the work or energy is only dependent on the initial and final position. For example, the gravitational potential energy of this marker, if it's at this height, it's going to be a certain value. So I can move this all around, and if I just put it at some position, some height above the Earth, it didn't matter how it got there or where it was. If it's at that position and it moved around and got there, came back to the same spot later, it will have the same potential energy. Same thing for a spring. If it doesn't matter if I have it at some compressed length and I move it all around and I go back to the exact same compressed length, it will have the exact same spring potential energy. So therefore it only depends on its position. Therefore we can have something potential energy. So therefore, potential energy and work are very closely related, but potential energy is path independent. So things like frictional force, if I have this marker move all around on my hand, and it starts at some position and it moves all the way around and comes back to the exact same position, well, the amount of energy or work that was acted upon between my hand and this object, the marker, depended on the path. I was spending lots of energy, so therefore it's not a conservative force. So therefore these potential energy are special ones. And therefore they're very convenient to write it in that form. If, for example, like the potential energy above the Earth's surface, MGH, or height above certain reference, or the potential energy in a spring. And so if we have a system, so this is the equation that I have. Now, if I have a system where only conservative forces act, so that's another thing, so the only thing that acts on my system is conservative forces. And therefore, conservative forces we know have, the way we rate them is potential energy. And if conservative forces act, then things are just initial and final position dependent. There's no like frictional force or some air drag force or something that affects it. So therefore, if only in systems were conservative forces, then this one can be simplified to say I don't have an external force, for example, acting on the system, because if I have a rope tied to this and pulling it, well, that's not a conservative force because that's is not path independent. So if I just have conservative forces acting, then this equation simplifies down and these terms go away to this form right here. So then I have my balance being so no heat was into or out of the system, no work was into or out of the system. I had no change in internal energy, just the conservative forces, therefore mechanical energy is conserved. So these are mechanical energy terms, but be very careful, you should never just write down that equation. You should only do that, for example, when you know that what assumptions I've made as far as that conservative forces are acting, there's no work into or out of the system, no heat transfer out of the system, no change in internal energy, and that's the only time where this is true. And then, for examples where that may be an applicable assumption could be an ideal swing, an ideal roller coaster, ideal spring, or mass drop from a vacuum. But we should never just jump to this as our equation, because we've made all these assumptions. But if all these assumptions are correct, then it's a very powerful equation. Going a little deeper into what work means right now. So work is for non-conservative forces, such as any external force acting in the system, so for example, friction, that is working on there while the part's in motion, moving. And so conservative forces, again, we'll consider those as far as potential energy terms. We won't double consider them. So work depends on the path. For example, if I have my system like this as I have some system, and it's going from going along this path, and it's going from some initial state to some initial position to some final position. So it's moving along there. There's going to be some external forces acting on my system, and so and at each moment of time, there could be an angle between the instantaneous path and instantaneous force, and I consider that as well. And also, I just can't consider this final position to that final position, initial position to that final position. For example, if the system goes along this path, going this direction, and then reverses and goes back, and it comes back and stays on that path, reverses, that needs to be considered in this integral term for work, because that's force while I have some motion going on. So it's just not the initial and final position. It's dependent. It depends on the path taken, including reversals. So work is from the initial to the final position along the path, including reversals, is the integral of the force, external force acting with a dot product to ds. And recall, a dot product is the cosine of theta. So my vectorial force, if it's in the exact same direction pulling along the path, the angle is 0. Cosine of 0 is 1. If the force is opposing the motion, the angle is 180, and the cosine of that is -1. If the force acting is perpendicular to the motion at that time, 90 degree, cosine of theta is 0. For example, let's say if I had a weight on a string and I'm swinging it around, and the force on the rope is like pulling towards the center, and the motion is going perpendicular to that. So then that rope force on that swinging weight does no work on it. Also, you kind of think about the moon and the earth, something orbiting. Now that's a potential energy term, and so you wouldn't consider it as work, but kind of the gravitational force and its motion are perpendicular. So there's no work being done on the system, okay, at the moon. So therefore, its potential energy is staying the same. Okay, it's staying the same distance from the Earth, because even though this force is acting on it, there's no work being done on it, and therefore its potential energy, initial and final states, would be the same. Okay, now let's consider a kind of a simple case. Let's make the path. Let's say something's called to the right here, the x-axis, and let's say the path is only along the x-axis, and I have some force acting on it. Again, it's just the vectorial component that's parallel to this displacement at that moment of time. So that would just be the x component, would be the positive or negative, that would affect the force. And then if I take the integral of this force dot dx, so this area under this curve is my work. Now, once again, if I have my object, let's say system's in the marker, and my hand, it's rubbing against my hand, and so there's some external force of my hand on the marker, and I start from this, and I'm just going how this going just in the x direction, and so the path is moving to the right. The force acting on the marker from my hand is to the left, so it's opposing it. So if it just starts here and it slides along my hand and ends up here, and there's some force acting on it, that integral is that work being done. But if it slides and then goes back and then slides and keeps going, so when it's going back, the path is in this direction, the force acting on the marker is in this direction, that's also doing work on it. So there's more work. So there's more work done on the pen, on the marker, if it does this kind of reversal kind of stuff from initial to final state, than it's just going from there to there. So therefore, it's path dependent. So therefore, it's a non-conservative force. And so in this graph shown here, I'm just assuming there's no reversals. But if there's reversals, then you must consider, just rather than just the x displacement, it's the x position is really the x displacement. So that really means x displacement on that axis. So you consider all the work done on this marker by the external force. And then let's say that frictional force is just constant in magnitude and a constant direction. Okay, then it's a constant magnitude. Then this force is just going to be constant, and so therefore it's the integral of this constant force term times the total distance moved, the total distance traveled in my time frame. That's the work done from the initial time to the final time. And if there's no reversals, if there's no reversals in the distance, then the distance would just be the initial minus the final minus the initial. So this force times the total distance traveled cosine of theta. Hopefully this was a good review of work energy for you.